About the atmospheric CO2, that's one of the graphics. We can already go into the graphics. I guess it fits into this moment. Is atmospheric CO2. We're past 400 parts per million.
Are you looking at the Zach Labe ones?
Yes.
The group of 4?
Yes. The atmospheric CO2 one fits into the conversation we're having now. I mean, essentially, that level of CO2 in the atmosphere is why everything is getting warmer. I mean, that's a dramatic escalation.
Yeah. I like how he put in, "You are here."
I know.
but you look at that, I mean, that's starting to look like an exponential curve. You look at that graph that he's got there, that is looking like an exponential curve.
And it's going back to like the 1600s, so you can see it's been pretty flatlined for a while. And the Industrial Revolution, right, in the 1800s, and you could see what's been going on.
At the start of the Industrial Revolution, about 1850 or so, plus or minus whatever number of years, it's below 300. Then we hit 350 at about 1980 or so. And with that, we've increased 60 ppms in about 40 years. Where how long did it take to increase from 275 to 325? That's 50 ppms. It took what, say 1780 to 1980? It's like 200 years.
You're right. That's a great point. I didn't think about that in this graph, because you could see how long the lines are versus that. Yeah, it's getting exponential. 1980. Jeez.
1780, 1980. Yeah, it's 200 years. Okay, so I want to make sure I can do basic arithmetic. But anyway, but yeah, I mean, it took 200 years to increase 50 ppm, and it's taken 40 to increase another 60.
Thank you. That's the right. Yes, that. What you just said was perfect. That explains this graphic.
You know, it's, and as I say, if you, I mean, I look at this curve here, and if I was to fit a function through that, I'd be looking to fit an exponential function through this data.
And I always say, like, it's gonna get worse, so buckle up.
Now, how much it increases, it depends on how long we continue doing the kind of stuff we're doing now with, you know, people working from home, Zoom meetings, and so forth. So that will definitely, at least for the short term, reduce CO2 emissions into the atmosphere from burning, you know, fuels for, automobiles. But there's the methane, there's the outgassing from the ocean. So I still would expect CO2 levels to increase. At what rate? That remains to be seen.
And we're not stopping, even though the COVID-19 issue has kind of hampered a lot of that down. But you know, we're starting to pick back up again.
Now let's look at the Arctic temperature ones, where 2-meter air temp anomalies.
The Arctic temperatures, yes, got it up by Zach Labe.
And you notice the baseline is 81 to 2010. So that's a 30-year baseline.
Okay, so 1981 to 2010. So
they're still recalculating for the new baseline of 91 through, or yeah, well, 2020 is not over yet. So 2021, they'll go to 91 through 2020 baseline.
Right.
Okay, just to kind of get a, you know, an idea of the reference plane there. So what's really cool about this is that you have data from 7 sources. That's what the R1, R2, etc. at the top is. So this is data from 7 sources. They track pretty darn closely, do they not?
They do.
So this is, first of all, this is excellent because you have, these are all independent agencies collecting their own data. And, you know, it's not exactly perfect between 1980 and basically 2005. It's pretty almost overlapping. And even till right to the present day, the only one that's kind of reading a little lower is the MERR2, MERRA2. It's the only one reading a little bit. It's still showing the same spikes and dips and so forth. So you have 7 independent agencies all basically telling us the same thing. Temperatures are increasing. And the up and down, of course, is seasonal variation.
And this is in the Arctic region, so
This
I
is
mean,
Arctic temperatures, correct. And if you were to fit a function through that, you would have a straight line that has a positive slope.
you could see the spike in the middle of the 2010s.
Yeah.
That's 3 degrees.
Guess what year that would be?
2016, 17?
2016, yeah.
2016, the hottest
Yeah.
drought in human history. Not
Yeah,
good.
2016. Yeah. So when you look at this, and if you look going back to 1960, okay, let's say 65 or so, we basically, there's from -2, and this is Celsius, from -2 to +2. So that's a 4-degree swing, and an average increase of 4 degrees C, which is 7.2 degrees Fahrenheit.
This isn't good. It's just not good.
And, you know, as we discussed before, when you look at the graphs over Siberia, you know, this red, all that warming, all that methane.
And this is the area that the air temperature area is, or just Arctic temperatures, is that gray circle. It looks like electricity, but it's a map.
Yeah, yeah, that's kind of looking down at the North Pole. So the North Pole being the center of that.
Well, you can see that area is warming 2 times faster than the rest of the planet, but
At least, yeah.
there was actually another Zach Labe graph. It showed that the red blob over Eurasia has now moved to the water. Did you see that? Probably, right? Zach is.
Well,
It was like,
I pulled a bunch of his up here for our discussion today. Let's see. Oh, that was last month. Maybe that's just this. Okay, that's that one there. I seen a whole bunch of things, you know, whether it was Zach or Rick or Brian, one of them, but I've seen a bunch were showing, you know, extreme excessive heat over Siberia, and that's moving into the Arctic Ocean. I've seen a whole bunch of crazy stuff,
yeah,
but
that.
I've also seen like cooler conditions coming down over the Canadian Shield. So we still have that persistent cooler conditions over the Canadian Shield.
And that would explain that strange snowfall and the winter blast coming down in May from like the northeast region of the United States. Is the cold air is pushed down, and like it's a big deal because the jet stream doesn't meander down in May, right? It's not supposed to. I guess average. It's not.
Well, it was interesting because Alaska was really cold this winter because the jet stream was very tight, so the
Right.
lower 48 was warm. Well, now we've got this warmth spilling over into from Siberia into at least half of, there's that bipolar polar bit again, but at least half of the Arctic. So that's weakening the gradients. Now it allows the jet stream to spill down again.
Oh, that's it. That's very interesting.
And it brings the cooler air and the lovely conditions. And
yeah, but what is the consequences of the Arctic? I mean, that is extreme red temperatures again. Jeez, and it seems like Alaska's in the red now. You guys are having a heat wave, right?
Well, it's like what we discussed before. It's going to affect the sea ice. Less sea ice is going to affect ice edge productivity. Okay, so we talked about how the warmth is spilling over into the Arctic, at least half of the Arctic Ocean basin. So that means the jet stream will now, because the gradient is less, will start dipping down. So that brings the cooler conditions to, lower latitudes. But the long-term effect, I think as you were asking, was the long-term effects, was that you have, you're gonna, the warmer waters is going to, store that heat, so that heat will delay sea ice formation, because the longer you have open water, the more energy that can be absorbed,
Oh.
as opposed to having ice that reflects the energy back out. So you have that going on. So high specific heat, etc. So sea ice formation is delayed, but with less sea ice in the first place, then you have less ice edge productivity, which is important for Arctic ecosystem. So that's going to be a negative impact. Then of course you got the methane issue and so on. And with more open water, when it does give off its heat, its cooler air temperature is going to create clouds, it's going to create more precipitation for that region. So you have this whole bunch of effects that happen down the line, and it all comes down to the heat being absorbed, the heat staying in the system.
And it's pushing the colder air elsewhere, but the warm temperatures are in the Arctic.
And even though that we were coming out of a very positive AO, we don't know what the AO is going to be like this winter. Could be positive again, probably will be, I think, but it could also be a negative, in which case we're back to that meandering stuff.
It just goes back to like last winter, right? That extreme polar, like the day after tomorrow snowstorm came after, like, the what is it, Chicago area. Whereas like this winter, it was really warm, but that's because it was a positive Arctic oscillation.
And had a very tight jet stream, very tight polar vortex. So it contained the cold up at high latitudes.
But then now it's finally in like spring, which is strange. I don't know, Jim. I mean,
yeah,
right around the corner.
I mean, this is kind of a good segue into the next couple of graphs. Let's look at the land ice.
Right, got it up. Land ice.
Okay. By the way, GT means gigatons.
Okay. GT.
Okay. So what we can clearly see going on is it's decreasing. And they're looking at Antarctica and Greenland. So these are the ice sheets, land ice sheet. It could be Thwaites Glacier, the West Ridge Glacier, et cetera, East Antarctic ice sheets and so forth. But so what they're showing is the graph is in 18 or so years is basically 3,000 gigatons fewer ice for Antarctica.
Oh, okay, it's a negative. It's showing a loss. Yes.
It's showing a loss.
Okay, yeah, that's shocking. I
mean, they could have done this as, like, say, X amount of total, say cubic kilometers of ice, and now it's this much cubic kilometers of ice, which is a lesser value. It's still a loss here. So they've just basically taken a baseline of whatever the amount was and saying, okay, how much less is it? It's about 3,000 gigatons less.
This graphic on the left with Antarctica shows that 2020 could possibly be the lowest land ice extent.
Yeah. And then look at Greenland. Greenland is like what, 4,800 gigatons less.
And that explains why the blue temperatures in the water around it, because the ice is going in the water.
That's right. That's why you have the ice melting, so it keeps that water cool. Same thing off Antarctica. Exactly correct.
And this is just shocking, because we might be within a few decades, you could argue, possibly no ice.
That thing definitely will be significantly less ice at present rates and condition.
We only have to wait 10,000 years for our dip back into the next ice age. So, buckle up for a warm summer. Good God, this is just...
Well, according to, if you look at the Milankovitch cycles, we should be going to conditions that favor ice growth.
Right. This is the impact of CO2.
So it's like, wow, we're really royally screwed on this one.
So naturally, we would be going back into an ice age. How like, a further deeper ice age. Maybe even deeper than the original ice age, right? Did you hear that?
I didn't.
Okay.
Can you,
That's just my imagination. And I just want that to happen. Okay. Bring back the woolly mammoth. Okay. Zach Lave, Arctic sea ice extent and volume.
Yeah, it takes us to 2019. It's still crunching the numbers for 2020.
Okay.
So on the left side, the extent, that's 10 to the 6. That's going to be 1 million, and then square kilometers. So, like 11 million square kilometers, 12 million square kilometers. So that's how you can read the volume there, the area. This is an area measurement. And this is usually done by aperture radar, SAR radar. So the radar flies over and takes the measurements, does calculations. So this is in square million square kilometers. So this is an area. And what we basically see since over the last almost 79 to 2019, that's 41 years inclusive, the endpoints there. And we've gone from basically almost 12.5 million square kilometers to basically 10.25 million square kilometers.
That's a lot of ice gone.
That's, so if you do the difference from, 12 and a half to 10 and a half, that's 2.5 million over 2 million. That's like 1/6. That's like 17% reduction. I'm just doing a quick math in my head here. That's like a 17% reduction.
That's like if 17%, I don't know if this is the right comparison, but 17% of the economy shrinking, if your currency was ice, I don't know. To conceptualize this is, it's amazing. It's shocking. The words, it's huge. It's a huge issue.
What is interesting, if you look at the two spikes in about, say, 2008 or so, then 2011 or 12 or so, see the two spikes there? That correlates to La Nina events and the changes in the Arctic Oscillation, where it promoted, at least for a little bit, some sea ice growth. I would expect that we would see something similar for what happened in 2020 before it went back down again, because we had conditions such as a positive AO or La Nina that promoted and tie in with the PDO, Pacific Decadal Oscillation, that gave conditions to allow some sea ice extent to increase. But as we saw, it was above the median this past winter, then quickly bombed down.
Right. Yeah, that graph we talked about, it kept going. It was above, and then it just dropped.
And then just went south. And now the volume is in 1,000 cubic kilometers. And again, over the 41-year endpoints included time frame, we're going from almost 26,000 cubic kilometers to, where is it about now? Say 14,000 cubic kilometers.
Jeez.
That's a far, 26 minus 14, that's 8 over 26. That's like 35% reduction.
Is the volume like the thickness?
Yes.
Okay.
Yes.
Yeah, okay. So not only is it shrinking in size, it's shrinking in like this way too, like being thinner and thinner.
So let's do an example. Let's say I have something basic. I have 2 meters by 4 meters. Okay, I look down from above. Okay, that's 8 square meters. Okay, but let's say it's 1 meter thick. Okay, so I have 8 cubic meters, but now it's half a meter thick. It's still 2 by 4. Right, I now have 4 cubic meters. Okay, just so this first one here is just looking at the area, the extent, how much it covers of the surface. This one takes into the volume takes into account how thick it is. Part of the reason we see such a drastic decrease is the loss of multi-year ice.